systems for electronic design automation. It's help to welcome David White.
So as some of you may know, at Cadence, we develop software, write software for electronic design. So my focus of my talk is going to be how we're using machine learning in our software, and how we're productizing machine learning for our software. So let's talk about some of the problems that we're facing in the electronic design industry. You can pretty much categorize all these problems into three buckets. The first is scale. We're dealing with larger and larger designs, more rules, more restrictions, and more and more data. So simulation databases are growing. There are larger and larger text files. And the other problem we're facing is complexity. We're dealing with more and more complicated silicon technologies like FinFETs, and more complicated design electrical rules. We're seeing a lot more interaction between chip, package, and board. And scale and complexity sort of compound to impact productivity, because we're also seeing more and more uncertainty. And more uncertainty leads to more and more redesign, and unfortunately for some, it leads to seamless schedules. There's a limited number of capable, trained design and layout engineers in the world, so you just can't throw bodies at the problem. You have to actually come up with ways to try to automate and improve productivity. So this slide shows sort of my view of how I think machine learning and deep learning will evolve for not only EDA tools, but for CAD tools in general. So the star sort of indicates where we believe we are today. So up to today, machine learning and deep learning has been used to primarily generate fast models. And as Rob mentioned in his talk, machine learning is really good for when you have a very complex, nonlinear problem, being able to develop a fairly simple computational model that runs very fast. And those are the type of applications you see in EDA today. So a couple of the examples I will talk about later is using machine learning for doing real-time parasitic extraction as you develop your physical design or layout. Another would be developing fast analog macro models for mixed signal simulation. So there are several examples in the EDA industry of using fast models. Today, I believe we're sort of on the cusp of developing what we call augmented intelligence, where we use machine learning to augment designer knowledge to improve productivity and turnaround time. And so these systems will learn from designers to tailor our tools to individual preference and individual design teams and individual design types. Okay? The next stage is what-if optimization. And here we start to use machine learning and distributed processing and optimization algorithms to do more what-if analysis, looking at, for example, alternative placement strategies or alternative routing topologies. And if you can couple these with very strong, powerful optimization methods, you can start to go off and you can start to find a more optimal routing or a more optimal placement in your layout or in your designs. And after we get through those stages, then we can start to use things like reinforcement learning to start to recommend multiple design steps or design sequences. And if we can recommend multiple design sequences to where basically the designer is just hitting accept to all of your recommendations, then you can start to automate large sequences of the design process. And eventually, we'll work our way to full machine automation. So the pace at which we're going to get there is dictated by a few things. One would be R&D, how much money is spent on R&D, and how much R&D focus these approaches get. The second is market acceptance, because some of these technologies will result in methodology changes. And as we all know, when you introduce methodology changes into design flows that have been around for many, many years, there's going to be some resistance to that change. So market acceptance is really important. And then lastly, our foundry partners. So foundry collaboration is important to making this flow happen. And so we need to have really, really strong collaborations with our foundry partners be able to make this happen as well. So in a lot of talks and articles, you'll see a focus on machine learning. But in most practical solutions that use machine learning or AI, there's very often 2, 3, or 4 of these tools you see here on the screen used. There's analytics and data mining for understanding what data should be used and how it should be used. There's, of course, the machine learning algorithms. And then there's large-scale optimization algorithms for how you can adapt and how you can build flexible systems. And I'll talk a little bit more about that in the coming slides. And then last, how do you fuel all of these tools using massive parallelization? So very often you'll see, like I said, 3 if not all 4 of these technologies at play in real products. Now this applies not only to EDA or CAD solutions, but you'll see these tools used across any number of different applications. IoT, as Rob mentioned earlier, and you'll see it across schedule logistics, transportation, finance, and many other systems as well. So how do we use these tools? Well, what you see here on the left is the software development process that we use at Cadence with my team. I've used the same process in the past in my prior companies for other applications. So it applies not only to CAD tools or EDA, but it applies to how to develop intelligent solutions in general. So the first phase is data preparation. Data preparation is one of the most undervalued steps in developing machine learning software. And I'll talk a little bit more about that in the coming slide as to why. The second phase is model-based inference. So it's just basically a fancy word for what algorithm you're going to use and how are you going to use it, how are you going to train it, and how are you going to test it. And then the third phase is adaptation. So once you've developed and trained your models, if you want to put them in real products, then you have to understand that when those products are released, they're going to be in environments that change. So your software has to be flexible, it has to be adaptive to those changes. And so adaptation is also very important. And that occurs in the operational phase after the software has been distributed and delivered to the customer, or in the IoT case, as Rob mentioned, after the product has already been developed and released into the world, how do you adapt to uncertainties in the environment? So data preparation. These steps aren't necessarily in order, so the first step is filtering. We all understand this. You want to improve the signal to noise. Okay, that's very important. That's kind of an obvious one. The second phase is augment. So how do you, especially when you have a heterogeneous set of data, how do you create a more uniform set of data, and how do you remove bias? This is particularly important if you're doing image processing, if you're in deep learning applications. The next is labeling. So it's very important to organize your data for training and analysis. So how do you tag the data, how do you cluster it, is really important. Now, Rob and I have given talks back to back so many times, I know his slides. So I'll allude to one of Rob's slides where he showed the bird with the frog in its mouth. And it said, is this a picture of a bird or a frog? So how you tag those photos is very important. If you want that photo to be classified as a bird, then you have to be able to distinguish that it's a bird from a frog, and vice versa. So how you tag the data is also very important. The next step is reducing the dimensionality of the input space. So reduction is very important because if you study machine learning, you know that if you can reduce the dimensionality of the input space, it generally would train faster and require less data to train. But there's a catch. You have to try to reduce the dimensionality of the input space while preserving the information content in the data. That's equally important. So there are a number of methods shown here on how you can do that. And then lastly, in data preparation, how do you partition your data? What data goes into the training set? What data goes into the test set, the validation set? So the second phase is the model-based inference phase. And here, we're basically going to select the algorithm we're going to use. There are many different types of machine learning and deep learning approaches out there, so you have to find the right one for your problem. Deep learning is a very interesting application, very interesting for many applications, but it's not the right algorithm for all applications. And so you have to basically be able to select which algorithm is correct. The architecture, figure out what parameters need to be set to, and then how are you going to train that algorithm? And then how do you test it? And then how do you validate it once it goes out into a larger system to be used? So these two phases are how we develop the models that go into our products. The next is, how do we deal with uncertainty once the product is released to our customers? Well, this phase is called adaptation. So what's most important is to know when the models you developed either are no longer valid or need to be adapted because something in the environment in which they work has changed. Right? So there's uncertainty and change in the world around us all the time. It's true in the software space as well. And so we need to be able to calibrate and detect when the models need to be updated. And then we need to be able to learn and be able to adapt those models to those changes. And then once we do that, we want to link them into larger optimization algorithms that allow us to do things like optimize sequences of decisions. Okay? And for that, we use things like reinforcement learning. And the reason I highlighted augmented here is because right now in our work, we're focusing on developing augmented systems that can learn from designers how to better design chips. Okay? So this flow shows how augmented intelligence works. So let's start with the data we have. So I work with the Virtuoso product. Okay, and in Virtuoso, we have circuit structures. We know what kind of circuit structure we're designing from your schematic design. We have the design requirements. And we also have a library of prior layouts for a given designer or a design team. Okay, that's the data we do have. And then we use that data to, laser's working, to develop our machine learning or AI models. Okay? And then we use those models to basically recommend various placement routing topologies, for example, to the designer. Now, the data we don't have, which is up here, is a lot of times the design intent or the design goals don't exist inside our software. They're in the designer's head, as well as the aesthetic preferences and some unique requirements. These are all things we cannot observe in our software, which means that we make our recommendations. There will be times that our recommendations will need to be updated or adapted, because as the designer chooses among our recommendations, we're going to learn using reinforcement learning and be able to train our models to better recommend, for example, in this example, placement and routing topologies in the future. Okay? So now I want to talk about a few applications of the development process you just saw. So I have a few slides to talk about these first three applications. I plan to talk about the fourth, which is using macro models for circuit simulation, because I anticipated that some papers that we had co-developed, co-written with some of our academic partners would have been accepted for publication. They're still in the process of being accepted, so I can't talk about the last one or show you any slides on it, but I can describe the application for you. Here we're using recurrent neural networks to basically capture the time-varying behavior in analog circuit types. And if we can do that, and if we can replace the analog simulation with a machine learning model that runs much faster, we can speed up mixed signal simulations much faster than we can today. So let me go to the slides that I can show. So we are using things like deep learning and convolutional neural networks to be able to detect hotspots or bad areas in layout. What we use is we take basically, as you see here on the left, sort of some training patterns here, which represent good training patterns and bad ones that have hotspots. And we train them using deep learning to be able to categorize ones that are good and ones that are bad. And you can see here for this example, we basically got 98% right, 2% wrong. So what's interesting is how deep learning actually breaks down layout into features and the features it extracts. So some of the features it extracts are obvious features, right? Source, drain, gate shapes, makes sense, right? N-type, P-type, makes sense. But there are some features that it extracts that, quite truthfully, just kind of boggle our mind as to what it is it's extracting. But it does work pretty well, as you can see here. Now, this is an IC-CAD benchmark because we focus mostly on real layouts, but I can't show you that data. So we actually took the IC-CAD benchmark data, ran it through our process, so we could actually generate data that we can show. But our results are pretty much in line with what you see here for the IC-CAD benchmark as well. The next example is we're using machine learning to capture, to extract parasitics in real time. And let me explain why. So in custom design, for many, many years, you do your schematic design, and then you go to the physical design stage where you're going to place your devices, you're going to route your devices. And it wasn't until you were done and you had a complete layout that you could run LBS, DRC, you could run your parasitic extraction, you could re-simulate it and see if electrically that design meets your original design intent. Now most often it didn't, so then you had to loop back through the layout and make changes to the routing or to the placement. So the problem we're solving here is we wanted to be able to extract the parasitics and electrically analyze the layout as it's being created, so that you catch the mistakes immediately and not have to wait to the end and then go back. And by doing this, we can improve productivity and deal with some of those problems we mentioned earlier in terms of scale and complexity. So the heart of this solution in Virtuoso is this machine learning model that does extraction, does parasitic extraction. Now this model has been in Virtuoso since 2013. So some of you actually may have used it, not knowing it was doing machine learning in the background. So this flow basically shows how it works. So when we generate our tech files at the Foundry, we have a big automated system. And that automated system has a field solver built into it. And then we have a number, we basically have a canonical set of interconnect patterns that represent the most common interconnect patterns in most layouts. We run those patterns through the field solver, which provides us with golden data. Provides us with coupling capacitance and total capacitance for that interconnect geometry. We use that data to train the machine learning models, and then those models get put into the tech file. So when that tech file gets distributed from the Foundry to all of our users, then they basically have the models, and then when the customer is doing real layout, the geometric profiles, as you're doing your layout, go through memory. Our models are in memory. The machine learning will basically process those shapes. It'll predict the capacitance and then display the capacitance and potential problems immediately on the layout. So the value here of using machine learning is that if you run a field solver takes anywhere between seconds to minutes or longer to extract one set of conductor geometries. We can extract a whole net in 1/100 of a second, so that we can actually do this in real time. And you can see the values, the accuracy down here, where we're shooting to have our accuracy be between plus and minus 10%, and you can see across all these corners that we are well within that. So this slide shows where we're going. Once we've built these engines for doing real-time extraction and analysis, we want to connect them up with optimization. Remember the one tool I mentioned earlier. Connect them up with large-scale optimization and massive parallelization to do electrically driven placement and electrically driven routing so that we can basically create correct by construction layout the first time as you go through the physical design process. Now we also use analytics because as we see more and more layout, our tools should get smarter. We should be able to understand your layout style. We should be able to understand your layout preferences. And the way we're doing that is to build analytics and a knowledge base that can start to tailor the tools to the particular design styles of our customers. So I'll wrap up with this slide here. So I've basically taught machine learning and AI courses over the last many years. And so I always get a question at the end is, well, how do I get started in machine learning? So I sort of added this slide into my talk. And there, as you heard in the earlier talks, there are a number of open source frameworks to help you get up and running very quickly. I provided here in the slide a couple of links to some tutorials that you can use. Again, you don't have to be a great programmer to get started as long as you can copy and paste from a tutorial into a Python command line. You can pretty much get up and running and get started. So I'd encourage you to try that. And I thank you for your time, and I'd be glad to answer any questions you may have.
Thank you, David. I know our audience really enjoyed your presentation, especially the part when you talk about massive parallelization. As a matter of fact, during your presentation, we received massive number of questions on parallel, and so I'm just going to present one because of the time constraint. So this person wants to know, at a high level, especially you presented in the White House before, right? Just pretend President Donald Trump is sitting here. What would you tell him? What's the overall trend of using AI in chip design? This is beyond Cadence and visuals, all the details.
Okay. Well, I think the next biggest wave, not only in chip design but in other applications as well, is how we can start to sort of connect in all of the advances that have been made both in software and hardware with a lot of the advances that are starting to be made in reinforcement learning. So you can actually start to build real learning systems. We're not just capturing mappings, but how do you build systems that can actually learn and improve themselves and adapt and optimize themselves? And I think that's probably the next big valuable wave in AI.
Wonderful. But before you take off, we're going to have Wei Xin, who is our co-chair of the annual conference. Okay, one more. I told you it's a massive number.
I'll be right back.
Thank you very much. Especially thanks for the example. I was wondering, to give an example, like what kind of algorithm, what kind of network you were using for the training that you showed the deep CNN. So my question is specific to this example, like how do you collect data and how do you make annotations for this data? And the model you trained, is it transferable as other model with that from internet? Is there any similarity for network that's used to the network publicly available?
So that's a very good question, and I probably have to give you a short answer. I'd like to give you a longer answer because it's actually a really good question. So there's a challenge in terms of how we capture layout as an image, because do you focus down at the device level or do you focus down at the circuit level? Which level do you focus at? And so we've been basically doing a lot of research and development on is to create sort of a basically windows of different sizes and trying to see where the optimal sized window is in terms of capturing layout as we sort of go, as we map, as we scan the layout to break it up into images like that. For lithography hotspots, it's a little bit easier because there's a certain range in which you need to look, and it's a more well understood problem. We're doing layout characterization in general. It's still a very active research topic inside our company. And then the second question you had was in model transfer learning. So we believe that if we can fundamentally break down layout that the features that we extract using deep learning will be transferable across a number of different applications. And so we believe there will be some model transfer learning that will go on, and that basically we will just train for unique applications. We would train those latter stages of the deep learning net and tailor it for particular applications. But the front few layers of the deep learning net would probably be very similar across many different, many different applications that would deal with layout. Great question, thank you.
Thanks again, David. So at this time, we have Wei Xin to present a token of appreciation to David.